Good morning, everyone. I will speak in this talk about the small mass radio regime, binary black hole evolutions with full numerical relativity. There is currently great interest in the binary black hole small mass radio regime. On one hand, the direct detection of gravitational waves from binary black holes, and on the other hand, the steady progress towards the establishment of LISA launch and the development of third generation ground detectors all highlight the necessity to expand the theoretical studies to much smaller mass ratios than we are currently used, limited to 1:1 to 1:10. A first proof of principle was performed in 10 years ago for a 100:1 mass ratio binary. The evolutions covered just 2 orbits before merger, and while they proved these evolutions were possible, the practical application of this kind of waveforms requires longer evolutions and ensure certain accuracy, of course. A new set of evolutions that we have recently performed are based on numerical techniques that have been refined for longer term evolutions of spinning, precessing binary black holes that were particularly tested for the case of mass ratios 1 to 15. We use this grid structure to study a sequence now of non-spinning binaries, starting from this 1 to 15 case, and then doubling each time the mass ratio and adding refinement levels around the smaller black hole. So we went to 115, to 132, 164, and we reached the 1 to 128 mass ratios black holes. That for about a dozen of orbits before merger. Fixed separation. This figure makes a comparative display of the 4 mass ratio waveforms, 115, 132, 164, and 128 at the bottom. You can see the decreasing in the amplitude of the waveforms, which are shown at the same scale, and the evolution time of each of the cases. Let me show you a table that displays the final black hole remnant in peak waveform properties. We also have a measure of consistency between the horizon remnant quantities for the final mass and spin, and the energy radiated in the form of gravitational waves as well as the angular momentum. Figure 3 displays comparative merger times for different mass ratios. In this table, we display the convergence rates for all the radiated quantities derived from the gravitational waveform. The detail of the conversion of the waveform phase and amplitude with global numerical resolution is shown in the bottom figure, displaying nearly 8th order conversion rate. We haven't enforced any alignment of the waveforms, should be clarified here. Another important part of the analysis is these remnant quantities, as I was saying, the final mass and spin of the black hole after merger, the recoil velocity, and at the peak of the amplitude, the waveforms have also a peak, associated peak frequency and luminosity that can be modeled depending on the mass ratio here for non-spinning black holes. And we have done this previously to these simulations using 1:1 to 1:10 mass ratios, and got fits that I will display in these slides. Those are the fits that are in color curves, right? And now the stars, the 4 stars, correspond to our new simulations: 15:1, 32:1, 64:1, and 128:1. So let me stress here that we use this fit on the blue dots and then extrapolate it to see where these lines would predict our simulations would be. So we haven't used our simulations for fitting here. I'm displaying just the extrapolation of the previous curve with the prediction for the mass, spin, recoil velocity, peak amplitude, peak frequency, and peak amplitude, so to say. So all of them lie very well within the predictions, which essentially also provide us with confidence about the accuracy of our simulations. So let me first make partial conclusions for this kind of studies. We have assessed the kind of errors we have with convergence rates, and also consistency of the horizon quantities versus the radiated quantities for up to mass ratios 1 to 128. We have assessed also errors for the remnant quantities and peak waveform quantities as extrapolated from more compatible mass ratios, and found that our studies correspond to errors at most of 2%. We believe that adding a spin to the large black hole is straightforward. We essentially can use just the same grid we have been using and provide a spin to the large black hole. Medium spin will be just the same run, essentially, accuracy. Of course, we can try to generate already some production runs for third generation detectors and LISA, with certainly good benefit of speed ups and large computational resources, but we see that these kind of simulations make possible to consider waveform banks. Since then, we have explored new gauges that actually we will see next produce better results. And we also started to look at these kind of simulations to support modeling of waveforms. For instance, allowing more parameters to be fit in the EOB NR project. So this is, I don't have much time to show this in detail, but this is kind of the fits we have been performing for the 128:1 mass ratio simulations. Now, still LISA could be sensitive to smaller mass ratios at 120. So 2 orders of magnitude smaller, for instance. This raises the question if numerical relativity can still provide accurate predictions for waveforms, trajectories, and final remnant, given such small mass ratios. So here we made a second set of studies with the current methods of numerical relativity, essentially introducing this new gauge and grids and and assessing new global resolutions. In particular, we use the moving puncture approach to test our formalism in a regime up to 1000 to 1 mass ratios. For the first prototypical study, we consider head-on collisions and compare them to the particle limit results. So figure 1 shows a first view of the results using a sequence of 7 to 1, 16 to 1, 32 to 1, up to 1000 to 1. In order to perform direct comparisons, we normalize the energy, essentially by dividing by 1 over q squared. We note the good agreement of the computed rescale radiated energy with the corresponding particle limit as we approach smaller mass ratios for all the mode displays, L equal 2, 3, 4, 5. We did note that the approach to the particle limit may depend slightly on the L value. So the larger L value, you have to go to smaller mass ratios to reach the particle limit. In a similar fashion, we display the radiated linear momentum that is somewhat more delicate because it couples L and L plus 1 modes. But also give us the opportunity to assess which are the minimal resolution required to reliably compute this linear momentum. We observed 8th order convergence where Q7 is actually over-resolved and Q 512 and 124 is slightly under-resolved for the lowest resolution used. A more detailed feature of the gravitational waves is provided by the spectrum of radiation. This gives us the opportunity to study the approach to linear regime as well as we move from Q7 toward Q16 and then up to Q124. We approach the particle limit here in continuous black line. And we have concluded that the numerical relativity and moving puncture formalism can effectively be used to compute a small mass ratio binaries, even in the 1000 to 1 and well into the IMRI-LISA territory, and can accurately describe those very low amplitudes gravitational waveforms. Thank you very much. Happy to answer any questions via chat or email.